Today in class we learned about the electrons, and this is going to be a shortened version of what we learned. Basically, we're going to want to teach you two things. I want to teach you how to do an arrow diagram, and I want to teach you how to do something called electron configuration. So that's the main two goals of today, is to learn how to do an arrow diagram and how to do electron configuration. The theory, now I will upload this PowerPoint so you can copy this, and anytime you need to pause, just hit the pause button and you can copy. But something called the quantum theory is what we're going to learn. This is a little bit more complicated than the Bohr model that you learned in middle school. But this is what an oxygen atom looks like, and so we're going to talk about looking at this and figuring out what all these letters and these arrows and things mean. So the topic is called the quantum theory. Back when we were dealing with Bohr actually said that the electrons are in nice little energy levels, but we actually know that is a little bit more complicated than Bohr made it seem. There's not just energy levels, there's actually sublevels, and we're going to look at looking at the sublevels and taking Bohr's model and making it a little bit more refined. This is what Bohr said sodium looks like. There's the nucleus, 2 electrons in the first energy level, then 8, and then 1 there to make 11 electrons. So that's when you were in 8th grade, that's what you would have drawn for Bohr. This is what the modern picture of sodium looks like. So again, just a little bit more complicated. We're going to talk about these orbitals and hopefully get you to understand what the modern theory looks like. Okay, first we talked about something called the principal quantum number, and there are 4 quantum numbers. We're just going to concentrate on the main one, which is known as the principal quantum number. It is going to be the letter N. Let me get all this out. There is a formula that we use. You click all this out, and if you want to pause right now, copy this down. If not, I'm going to keep going. That way the video is not that long, so you can pause right now, copy this down. The principal quantum number is basically the energy level, and to figure out how many electrons a certain energy level can hold, you basically use this formula, 2n squared. And 7 is the biggest that we're going to get for energy levels, so in order to figure out how many electrons each energy level can hold, you replace the n, which is the principal quantum number, with the energy level. For example, you would, instead of putting n, you would put a 1 for first energy level. And you always square the number first, so 1 squared is 1 times 2, and the first energy level can hold 2 electrons. If we do that for the next one, 2 squared is 4, 4 times 2 then is 8. If we do it for the third energy level, we're going to replace that. 3 squared is 9, 9 times 2 is 18. So you probably learned 2, 8, and 18 in middle school. 4 squared is 16, 16 times 2 is 32. 5 squared is 25, 25 times 2 is 50. 6 squared is 36, 36 times 2 is 72. And then 7 squared is 49, 49 times 2 is 98. So if you were asked on your quiz the maximum number of electrons that a certain energy level can hold, the maximum number, you would just replace the n with the energy level. So if I gave you the 4th energy level, you would change that to a 4, and you square it first, and then multiply it by 2. So not real hard. When you were in middle school, you learned that the first energy level filled up, and then it went on to the next one, and then went on to the next one, filled that one up, went on. But honestly, that's not true. Something happens past element number 18. And past number 18 on the periodic table, you get some craziness. You get some crazy jumping around going on. So, and it has to do with energy, and that's going to be my explanation, but I can go a little bit more detail later, but it has to do with energy. Okay. So these subshells, there are 4 of them. And this makes up the second quantum number. And this is S, P, D, and F are our 4 subshells. You may want to pause again right here and copy all this down. But I'm going to go ahead and go on. Okay. An S subshell, there are 4 different subshells. An S is basically just going to be a sphere shape. It's said to have 1 orbital. What an orbital is, 1 way to turn it. You can only turn a sphere one direction. You can't change it on the x and y axis because it's a sphere. It's the same all the way around. What I need you to understand is the S's can hold a pair of electrons. So the magic number for S is 2. It can hold 2 electrons. In a moment, we're going to be doing some arrow diagrams, and for S's, we're going to be drawing something for the orbital. And one way we could do it is to draw out those spheres. Another way is to just draw a blank. Since it has one orbital, we're going to be putting one blank for S's. P's can hold 3 pairs of electrons because they have 3 orbitals, so we're going to be putting 3 lines for those. This one has 5 lines. And this one has 7 lines. That's how many orbitals it has. 1. Alright, so then each orbital can hold 2 electrons. We're going to be drawing electrons in our little arrow diagram with arrows, hence the name arrow diagram. The arrows are going to illustrate electrons. And so what we do, in a certain orbital, there can be 2 electrons. We're going to draw one of them up and one of them down. What that's going to mean is they're going to be spinning in opposite directions. If you put 2 negative people in a very small space and told them to run around, they're probably not going to run into each other. They're going to stay as far apart as possible. And we say one spinning clockwise and one spinning counterclockwise. That will show up on the next PowerPoint. So S can hold 2 electrons. P can hold 3 pairs, so you can put, I'm going to draw them like this. They actually spread out first, and then they come back and double up if they were necessary. So it's going to look like this. So the magic number for P is going to be 6. So S is going to be 2. P's are going to be 6. These can hold actually 10 electrons. And notice I'm spreading these out, and I'm doing this for a reason. They spread out, and then they come back in and fill. It's kind of like if you had 5 empty seats on a bus. If you had 5 people, they would all spread out, especially if they didn't like each other. And then they would only double up if necessary. D's can actually hold 10 electrons, so the magic number is 10 for D. And then F's can hold 14, so there's, again, I'm going to spread those out. And this is the way our arrow diagram is going to kind of look. So this is 14. Okay, so if I say S, you're going to say 2, P is 6, D is 10, and F is 14. And we're talking about electrons. This whole story is about the electrons. Now I drew, let me skip here. I drew blanks, but this is really what it looks like. This is an S, and so there's only one way to draw that sphere, so we drew one blank here. In that, our 2 electrons are spinning opposite, so that's why we did one up and one down here. These are the P's. Notice there's 3 different ways, so we drew 3 blanks here. And basically, the electrons spread out, and then if they were to double up, they double up this way. And so they spread out, and then they double up if necessary. And then these are crazy shapes, but notice there's 5 different shapes for D's. So we drew 5 blanks, and for these are 7, so we drew 7 blanks. Now if you want to draw these pictures instead of drawing the blanks, you can. But this what's what the blanks are representing. So the S has just this one sphere shape. The P's, we say they're dumbbell. To me, they kind of like a peanut shape, balloons with lobes. And you guys might have studied the X, Y, and Z axis. The X and Y, you graph that all the time. The Z axis is actually 3-dimensional coming out at you. So that's why you actually see X, Y, and Z there. This is just illustrating. There's the Y-axis, there's the X-axis, and here's the 3rd dimension axis, Z, coming out at you. So that's why we have 3 different shapes. There's 3 different ways to align those P orbitals and those D orbitals and those F orbitals. So you may want to copy this. It says electrons are said to spin in opposite directions from one another. We say that one spins clockwise and one spins counterclockwise. So we show that by one arrow up and one arrow down. That's just to illustrate that they're going to go opposite one another. So now we're going to move on. Alright, I gave them this in class to kind of help them see, to put the 2 theories together. Our brain kind of likes the Bohr model a little bit better. And so the Bohr model are these nice little rings going on here. We actually know they're not really true rings anymore. It's actually more of a distance. So the first energy level is a closer distance than the seventh energy level, etc. And then this is the new model, which is the S. The first energy level can hold 2 electrons. So notice that we have an S. Remember, the magic number for S is 2. So I can actually put 2 electrons here. Second energy level can hold 8. The magic number for this was 2. The magic number for this was 6. And 2 plus 6 is 8. The third energy level has S, P, and D orbitals. And remember, they're using boxes for this, and I use the blanks because I'm a little bit lazy. S's can hold 2, P's can hold 6, and D's can hold 10. And if you add those up, you get 18. S's can hold 2, P's can hold 6, D's can hold 10, and F's can hold 14. If you add those up, you get 32. So you should start to see a pattern from what we did on the slide a minute ago. Alright, we're going to do just a few, and then I'm really going to spend more time teaching you how to do this, reading from the periodic table, than actually doing this. We're going to do a very small atom. I'm going to do like 4, and then I'm going to move on to the periodic table. Alright, so if I were doing hydrogen, hydrogen's number 1 on the periodic table. We're going to assume that all these things are neutral. Neutral means they have the same number of protons and the same number of electrons. And this is all about the electron. This is our nucleus in the very center. Hydrogen's number 1, so he has 1 electron. So his 1 electron is going to be right here. And what that means is in that first energy level. So we're going to do 2 things. We're going to do an arrow diagram, and we're going to do an electron configuration. So if I were doing hydrogen here, there's 1 arrow, and it's in the S, and it's in the first energy level. So the very first thing we write, we're going to write a 1, and that means first energy level. That's like the old Bohr model. The second thing we're going to write is the subshell, which is the S. And then how many electrons are there? There are 1. So this is our energy level. This is the sublevel, and this is how many electrons are there. So when I go to draw this for this is called the electron configuration. It's like an address for the electron. It works like this. You're going to make a 1S, and then you just draw 1 arrow. That's called the arrow diagram. Electron configuration, arrow diagram. Alright, so now I'm going to do a few more. I would like to do carbon. Carbon's number 6 on the periodic table. That means he has 6 electrons. Well, there's 1. I get ready to put 2. It's going to go here. So there's number 2. If I go to 3, now this is full, so I got to come out here. So there's 3. Well, here's 4. I've got 2 more, so I'm going to be putting them here. But just as I talked about before, if you have 3 empty seats on a bus, which is what we've got going on here, 3 empty seats, those electrons don't like each other. They're negative, so they're going to spread each out. And so we would spread them out. You don't have to spread them completely out by putting 1 over here and 1 over here, but just need to put them in different locations here. Alright, so when I get ready to write this, you start here. This would be 1, and this is an S. And in that box, there are 2 electrons. Then we move on. This is the second energy level, so we put a 2. This is an S, and there are 2 electrons. And then we move on. This is still second energy level, so we put a 2. This is no longer an S, it's actually a P. And then there are 2 electrons here. I'd like to point out something. 2 plus 2 plus 2 add up to 6. These numbers always add up to our atomic number when we're talking about a neutral atom. So when I draw the arrow diagram, it looks like this. I go 1S, an up and a down arrow, and then I go a 2S, and I go an up and down arrow. I'm almost repeating this. For P's, I'm going to draw 3 blanks because it's illustrating those 3 orbitals at which P can have. And then this is 2P, and then I'm going to spread it out. That's going to look like that. So again, this is electron configuration, 1s2, 2s2, 2p2, and this is called the arrow diagram. Alright, I'm going to do a couple more. And then we're going to learn to do from the periodic table, which is where a lot of the classes got stopped because the bell rang. I would like to do argon. I did argon with them in class. Argon is number 18. Okay, so I'm at 6. There would be 7. Here's 8, 9, 10. So you got to that magic 6, got to move on. So there's 10, there's 11, there's 12, there's 13, there's 14, there's 15, there's 16, there's 17, and there's 18. So when I get ready to write this, I would start here, and it'd be 1s2, then it would be 2s2, then it would be 2p6, then it'll be 3s2, and then it'll be 3p6. There's that's called the electron configuration. If I add these together, you'll get that magic number of 18. The arrow diagram is going to look just like that. One up, one down. One up, one down. P's have 3 legs. Go up, we go up, we go up. We go down, we go down, we go down. And then we got 3s, we'll go up and we'll go down. For p's, we got 3 legs. We go up, we go up, we go up, we go down, we go down, we go down, 3p. So there's the arrow diagram. So if you can write out the electron configuration, then you're just kind of redrawing for the arrow. We won't do a lot of the arrow diagram, but I'm just wanting, it will help us illustrate, and the EOC might actually have some pictures of some arrow diagrams, so I want you to know that. Okay, so I want to do, now we're going to move on to potassium. Potassium is number 19, letter K, number 19 on the periodic table. And if you were listening a second ago, I said once we get past number 18, some craziness starts happening. And what the craziness is we would think that the number 19 electron would go right here, but honestly is what it does. It goes out here. It has to do with energy. It is less energy for the atom to put into the s orbital, which is a nice little circle, than to start filling those weird orbitals, which are the shapes of the D. The analogy I give, some of you may have ran track before. These are like track lanes, lane 1, lane 2, lane 3, lane 4. If the coach gave you a choice, he says, okay, guy, you can run a mile, and you can run in lane 3, but I want you to run in all those weird shapes. If I go back, you remember all those weird shapes that the D's were in. Let me flip back. You can run that, but you got to run in this pattern. Or you can run just a little bit further out in the next lane, and you can just run in a circle as you go. So what do you think is easier, run in a circle or run in these weird patterns? Well, it's a lot harder to run in these weird patterns, so it requires more energy. So this requires more energy, so it actually jumps out here. So when I write this one, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, and then it becomes a 4s1. And then we would just draw the arrow. So I'm not going to draw the arrow diagram for this, and we'll do some of the other ones in a moment. Okay, so now if we did calcium, calcium would actually look like this, which is number 20, and this would change to a 2. But now when I get ready to do number 21, which is scandium, which is SC, number 21, well, rather than fill the P, it actually falls back down and fills that. And so when you write it in the order at which it fills, and it filled 1s2 first, 2s2, 2p6, 3s2, 3p6, and then it went out and filled this one. It becomes 4s2, and it becomes 3d1. Again, I can add these numbers up and see if they equal 23. If they don't equal 23, then I've done something wrong. Now in the arrow diagram, this one's getting a little bit big. I'm not going to make you do arrow diagrams for really large ones, but I would just do it as 1s up and down, and I'd have 2s up and down. P's, there's 3 of them, up, 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 down, down, down. Then you have 3s, up, down. We're going to run out of room, and this starboard doesn't let me go very far over on this. I have to be on a blank page to go far. So I'm on 3p, And again, that would be up, 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 then down, down, down. I'm going to come down here. Then we have 4s, up, down. And D's, I don't want you to just draw one. There's 1, 2, 3. Whoops, can't draw anymore. I wouldn't be, well, let me scoot that. I should have started over here. Let's go this 4s, up and down. For the D's, you draw 1, 2, 3, 4, 5. But you're only going to put one arrow in that. But I want you to see that there's available space, because we're about to start talking about bonding, and that's the reason we're doing arrow diagram, because you can see maybe it's going to lose some electrons and where it's going to be losing electrons from and why things are going to be a little bit different sometimes. So I wanted you to see, so it's kind of important to see the arrow diagram. Alright, now we're going to move and look at the periodic table. If you keep clicking through the PowerPoint, you will see an explanation of this. This is the energy level known as the shell. This is the subshell, and that's how many electrons there are. This was hydrogen. Click. Here's one of carbon. Carbon is 1s2, 2s2, and it's going to be a 2p2. The s's are circles, so here's 1s, and here's 2s. And P's start getting to be those weird balloon shapes. So what you're seeing are the P orbitals here. There's only 2 electrons, but there's space for others. But notice this one says empty, because there's nothing in there. So I don't know why up here it says Z is empty, but over down here it's got Y is empty, but that doesn't matter. Okay. So again, this is the same stuff going on. This is showing the arrow diagram. Okay, and that's the way oxygen looks. This is the elements as they go in the periodic table, and this is what they look like. Notice that 1 means first energy level, it's just a circle. 2, first energy level, just a circle. You start adding P's, you start adding those more complicated shapes into there. So this is what we're going to start seeing. Okay. This right here, you're going to want to copy. If you haven't come by to get a blank periodic table from me, you're going to want to copy this. So if you're at home and you got a printer, this would be a good one to go ahead and print off, or you can have. You might not want to print it in color. It doesn't need to be in color. But this is a little pattern on the periodic table. S's can hold 2 electrons, and if you'll look here, there are 2 blanks where I've written S's. You notice this little element here, this is helium. He actually belongs right here in this little clear spot right there. Hydrogen's 1s1, helium's 1s2. So everything in this first family, known as the alkali metals, they all end in s1. Some of them end in 2s1, 3s1, 4s1, 5s1, 6s1, or 7s1. But here that in the second blank they would end in S2. So this would be 2s2, come on, 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. And P's can hold 6 if you count your blanks here. 1, 2, 3, 4, 5, 6. Here is P1, P2, P3, P4, P5, P6. All your noble gases, with the exception of helium, because he really kind of belongs right there, they all end in P6. D's can hold 10. D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. See a pattern going on? And F's can hold 14. If you count here, those are 14 blanks down there. This is what the periodic table would look like if we were to take that lanthanide and actinide and pull them up into the periodic table. They would look like this, but the problem with that is it would throw the whole periodic table off. So because of that, we pull them down, but we can't forget that they're down there. Let me go back once. We are going to, hope you have this written down, we're going to learn how to read from the periodic table. And the periodic table actually shows the skipping that's going to take place. Because you're going to read it like this. You're going to go through 1s, then you're going to go 2s, 2p, 3s, 3p, it goes 4s, and then it goes 3d. Then it goes, oh goodness, board is not wanting to cooperate. Then it goes 4p, and then it goes 5s, and it goes 4d, then it goes 5p. So if you can learn to read the periodic table, this is going to be so much easier. So let me go. And you all have a periodic table that looks kind of like this. I'm going to minimize that. Let me switch to a color that red's good. Do you see the numbers here, 1 through 7? Those are the numbers that go in front of the S. So it's 1S, 2S, 3S, 4S, 5S, 6S, 7S. Over here on the P's, you don't see numbers, so I suggest you do write them. This would be 1, this would be 2, this would be 3, this will be 4, this will be 5, this will be 6. Those are also the numbers that's in front of your P's. P's are over here. In the middle are where your D's are hanging out, and D's are weird because of the way the thing skips around. These are 4S. The D's actually start numbering with 3D. This is 3D, this is 4D, this is 5D, and this is 6D. And down here, I call them my AEP elements because they can't really behave because they disrupt the periodic table. This is going to be 4F, and this is going to be 5F. Okay, so we're going to pick a few easy ones, and then we'll go a little bit harder. If we were trying to do, well, since this one's hanging out here in front of us, if we were trying to do silicon, which is right here on the periodic table, if I were trying to get to number silicon, number 14, and I wanted to write the electron configuration, first off, helium belongs right here in this blank, because he is an S2, because he has 2 electrons, he's a 1s2. Okay, so I'm just going to kind of move him just where we can see. I've got to start and go through these 2 blanks, and I'm trying to get to number 14. So you would go here, and you would be going through 1s, and you're going through 2 of them, so it would be 1s2. Notice I moved him. So then we're going to go through number 3 and 4. So now this would be 2s2. Then I'd be going through all of these, and these are the P's, and they're the same as whatever row I'm on. So this is 2p6, and then I've got to go through these 2, and it would be 3s2, and then I'm at number 12, so don't jump down here to 21 and stuff. Then I go 13 and 14, and this will be 3p2, and I can count those. That's 2 plus 2 is 4, plus that is 6, plus 12 and 14. And then I could simply mimic and do the arrow diagram underneath it. There's that one. There's that one. 1, 2, 3 for that one. Up, 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 down, down, down. Then I go up, down, 1, 2, 3 for P's, and I'm only going to put 2 in them. Now I'm going to separate them out. And then we just put the labeling underneath it. So that's called the arrow diagram. On the homework I have you do both. Alright, let's do a couple more. Alright. Let's see. Alright, if we wanted to do, I don't know, let's do vanadium. Number 23. Trying to get through 23, so I got to start out, I got to go through number 1 and 2. So I'm doing vanadium, number 23. He would be 1s2. They all start with 1s2, except for hydrogen, he's 1s1, but everyone else starts with 1s2. So then I go through those, now I got to go for 3 and 4, so then that would be 2s2. Then I've got to go through these, and that will be 2p, and I'm going through all blanks, 1, 2, 3, 4, 5, 6, remember P, the magic number is 6, and then I'm going to move down here, and this will be 3s2, just keep going, I'm going to go through 13 through 18, which will be 3p6, going to keep going, this was going to be 4s2, and then this will be 3d, and I'm stopping to count the box that you actually end up in, so 3d3, and again I just add those up. That's 2, that's 10, that's 18, that's 23, and it should add up to your atomic number. Alright, that's electron configuration, that's the arrow diagram, and learning to use the periodic table. We'll go further on this in class, but if you missed today, at least you should be somewhat caught up. And there is a practice worksheet, and if I will upload that to Edmodo as well. There are 15 problems, I do believe. In the first 10, you're doing both. You're doing the arrow diagram and the electron configuration for. And then the last ones, you're just doing the electron configuration. So hopefully, if you were in class and you were a little bit lost, this might help you. We will be talking about it more, explaining it more, talking about all these numbers and stuff mean. But that's called the electron configuration, which basically just shows where the electrons are. Okay, have a good evening.